Today we are covering two vital areas of the IB Mathematics Analysis and Approaches higher-level syllabus, counting principles and the extension of the binomial theorem. In this lesson, you will learn to distinguish between permutations and combinations, expand binomials with negative or fractional indices, and determine the range of validity for infinite series. Mastering these topics is essential for securing a grade 7. Combinatorics forms the backbone of complex probability questions in Paper 1 and Paper 2, while the binomial extension is a frequent feature of higher-level calculus and series questions. In combinatorics, the most important decision you will make is determining whether the order of selection matters. When the order of arrangement is important, we use permutations. Think of a race where coming first, second, or third results in different medals. The number of ways to arrange R objects from a set of n distinct objects is given by NPR. Mathematically, this is n factorial divided by the quantity n minus r factorial. However, if we are simply choosing a group where the position within that group doesn't change the outcome, we use combinations. For example, picking 3 friends to go to the cinema. The formula for NCR, also written as n choose r, includes an extra r factorial in the denominator. This extra r factorial effectively divides out the different possible orderings of the same group, because in a combination, those orderings are considered identical. Let us apply this logic to an example of a club with 10 members. First, imagine we need to choose a president, a secretary, and a treasurer. Because the roles are specific, the order of selection matters. Choosing Alice as president and Bob as secretary is different from choosing Bob as president and Alice as secretary. Therefore, we use a permutation. We calculate 10 factorial divided by 7 factorial. The 7 factorials cancel out, leaving us with 10 times 9 times 8, which equals 720 ways. Now, consider part B. We need to choose a subcommittee of 3 members. In this case, the members are equal. There are no specific roles. The order does not matter, so we use a combination. Notice how we divide the permutation result by 3 factorial, which is 6. This gives us 120 ways. In standard level, you worked with the binomial theorem for positive integer powers, which results in a finite number of terms. However, for higher level, we extend this to a general index n, which can be a fraction or a negative number. The formula for the expansion is given as 1 plus x, all to the power of n, equals 1 plus nx, plus n times n minus 1 over 2 factorial x squared, plus n times n minus 1 times n minus 2 over 3 factorial x cubed, and so on. When n is not a positive integer, this expansion does not terminate. It becomes an infinite power series. Because it is infinite, we must ensure the series converges to a finite value. This expansion is only valid when the absolute value of x is less than 1. If x were greater than 1, the terms would grow larger and larger, and the sum would not exist. If the binomial isn't already in the form 1 plus x, you must factor out the first term, a, to create that leading 1. We rewrite it as a to the power of n multiplied by the quantity 1 plus b over a, all to the power of n. The validity condition then becomes the absolute value of b over a is less than 1. Example: expansion of a square root. Let's find the first 4 terms of the expansion of the square root of 1 minus 2x and state its range of validity. First, we rewrite the radical as an exponent. Here, our index n is 1 over 2, and our variable term is negative 2x. We substitute these into the general formula. Now, we simplify term by term. The first 4 terms are 1 minus x minus 1/2 x squared and minus 1/2 x cubed. For the expansion to be valid, the absolute value of our variable term, negative 2x, must be less than 1. This simplifies to the absolute value of x being less than 1/2, or x being between negative 0.5 and positive 0.5. Notice on the graph how the red dashed approximation closely follows the blue curve near x equals 0, but begins to deviate as we move toward the boundaries of validity. The extended binomial theorem is an incredibly useful tool for dealing with rational functions. In IB higher level, you will frequently be asked to expand functions that look like fractions, such as 1 over 1 plus x or 1 over 1 minus x squared. By rewriting these fractions with negative indices, we can apply the same power series formula. This allows us to approximate complex rational functions with simple polynomials. Let's look at an example. We want to find the expansion of 1 over 2 plus x up to the term in x squared. Step 1 is to factor out the constant. Recall that the formula requires a leading 1, so we must factor out the 2 from inside the bracket. Factor out the 2, which becomes 2 to the power of negative 1 outside, leaving us with 1/2 times 1 plus x over 2 to the power of negative 1. Now for step 2. Expand with n equals negative 1. We replace our variable in the formula with x over 2. Applying the formula, we have 1/2, then 1 plus negative 1 times x over 2, plus negative 1 times negative 2 over 2 factorial, times x over 2 squared. Step 3 is to simplify the terms. Inside the bracket, we get 1 minus x over 2 plus x squared over 4. Distributing the half gives us the final expansion, 1/2 minus x over 4 plus x squared over 8. Finally, we must state the range of validity. The expansion is only valid when the absolute value of the variable part, x over 2, is less than 1. This simplifies to the absolute value of x being less than 2. So this series only works if x is between negative 2 and 2. Let us tackle a typical IB-style higher-level question that combines these skills. Find the first 3 terms in the expansion of 3 over the square root of 4 minus x, and state the range of validity. First, we rewrite the expression in a form suitable for the binomial theorem. Next, we must factor out the 4 to get a leading 1. This is where many students lose marks. Since 4 to the power of negative 1/2 is 1 over the square root of 4, which is 1/2, the expression becomes, now, apply the formula for n equals negative 1/2 and replace the variable with negative x over 4. Simplify the terms inside the bracket. Distributing the 3 over 2 gives the final expansion. Finally, the range of validity. We check the absolute value of the term we substituted. The expansion is valid for x between negative 4 and 4. Let us look at where students often lose marks in these topics. When expanding an expression like the square root of 4 minus x, many students immediately use 4 as the first term. The formula only works for a leading 1. You must factor out the constant first, and remember to apply the power to that constant. If your binomial is 1 minus 2x, your variable term is negative 2x. Forgetting that negative sign will lead to incorrect signs throughout your entire series expansion. In combinatorics, students often use NPR when they should use NCR. Always ask yourself, does the order change the outcome? If the group is the same regardless of order, it is a combination. Now, let's look at some important exam tips. In the IB, even if your final simplified expansion is wrong, you can gain significant method marks by clearly showing the substitution into the binomial formula. Write out the formula with brackets before simplifying. Always check if the question asks for the range of validity. It is usually worth 1 mark at the end of a long question. If you used x over 4 in your expansion, your validity is the absolute value of x over 4 is less than 1. For non-calculator papers, practice simplifying factorials mentally. For example, 10p3 is just 10 times 9 times 8. You don't need to calculate the full factorials. It is time to test your understanding. Please pause the video and attempt these 3 questions. Easy. Find the number of ways to select a team of 4 players from a group of 12. Medium. Expand 1 plus 3x to the negative 2 up to the term in x squared and state the range of validity. Hard. Find the coefficient of x squared in the expansion of 1 plus x over 1 minus 2x cubed. Pause the video now. Let us go through the solutions. For the easy question, since we are selecting a team and the order doesn't matter, we use combinations. 12 choose 4 equals 12 times 11 times 10 times 9 over 4 times 3 times 2 times 1, which simplifies to 495. For the medium question, we use the formula with n equals -2 and replace x with 3x. 1 plus 3x to the negative 2 equals 1 plus -2 times 3x plus -2 times -3 over 2 factorial times 3x squared, which equals 1 minus 6x plus 27x squared. The validity is given by the absolute value of 3x being less than 1/3. For the hard question, we treat this as 1 plus x multiplied by the expansion of 1 minus 2x to the -3. First, expand 1 minus 2x to the -3 up to x squared. This gives 1 plus -3 times -2x plus -3 times -4 over 2 times -2x squared. Now, multiply by 1 plus x. We look for the terms resulting in x squared. The x squared terms are 24x squared and 6x squared, giving a final coefficient of 30. To finish, let's summarize the essential points from today's session. In counting problems, always identify if the order of selection creates a unique outcome. If yes, use permutations. If no, use combinations. For binomial expansions with negative or fractional indices, you must factor out constants to ensure the expression is in the form 1 plus x. Remember to apply the exponent to the factored constant. Unlike integer expansions, these series are infinite and only converge when the absolute value of the substituted term is less than 1. This step is a common source of marks in IB exams. Small errors with negative signs and fractions can propagate through an entire series. Use brackets during substitution to keep your working clear and maximize method marks.